All right, Unit 2B, Day 3. It's all about the natural base E. I have this written out. 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3. And it continues on forever and ever. So as you can see, I'm adding these all up, which is a series. And when you add them up, you get an approximation, which is 2.7182818, and it continues on forever and ever. And that is what is the number E. Kind of like pi, it's an irrational number that continues on forever and ever with no pattern. Same with the number E. And E's approximation is 2.718, and that's what we'll use for when we're rounding using E. Your calculator, though, does have an E button. So if you were to look at that, you would see it. And it'll use the full decimal. But E is approximately 2.718, just like pi is approximately 3.14. So we are going to start working with this natural base of E to help us get ready for continuous growth with money problems and interest problems, as well as logarithms that are coming up soon. So my suggestion is to watch the video, take notes, and then come back and just watch it again and listen more carefully. So we're first going to start with the number E, just doing some rules of exponents. So if we wanted to simplify e to the second power times e to the fourth, your rule of exponent tells you when you're multiplying like bases, you add your exponents, and that'll end up being e to the sixth. Okay. Number 2, if you had 2e to the third power all raised to the fourth power, that's like a power to a power, which we actually talked about the last couple days. This is the same thing as saying 2 to the fourth times e to the third to the fourth. And what you do when you use your power to a power rule, you multiply those exponents. So this becomes e to the 3 times 4, which is 12. And then 2 to the fourth is going to give you 16. Okay, so this first one is your multiplying like bases. And then this rule here is your power to a power rule of exponents. Number 3, if we were dividing, so let's say we had 12e to the fifth power all over 3e to the second. You're going to treat the 12 divided by 3 like you normally would. And then for your powers of e to the fifth divided by e squared means you're going to do e to the fifth 5 minus 2 power, which ends up being 4e to the third power. And that's the quotient rule of like bases. Okay, so these are all rules of exponents. A little review from Algebra 1 here. And our like base in all of these is E. Okay, and then we'll do one more with a square root function. So if we have the square root of 25e to the 8th power, we can separate that into the square root of 25 and the square root of e to the 8th. The square root of 25 is 5. And then the square root can be converted over as an exponent as a 1/2 power. So if it was square root, it can be 1/2, cube root, 1/3, fourth root, 1/4. And then you use your power to a power rule and you multiply those exponents. 8 times 1/2 becomes e to the fourth. Okay, the last thing for today that we're going to look at is graphing exponential functions. So let's just look at y equals e to the x. just like when we practice exponential growth and decay, the first point is when we plug in 0. E to the 0 power is 1. Remember, anything to the 0 power is 1. So you have the point 0, 1. And your other point, if you plug in 1, e to the first power is itself, which we know is approximately 2.718. So we can just go a little bit between 2 and 3. And you have the point 1, e. And this looks just like your exponential growth function because e is greater than 1. So e to the x is an exponential growth. It has a base of e, which is 2.718. It still has that horizontal asymptote. Okay. Your domain is all real numbers. Your range is 0 to infinity. And if we look at end behavior, just like we did with exponential growth and decay, as x gets really small, meaning going to the left, you can see the function approaches 0. And as x gets really big, meaning going to the right, y goes up to infinity. So it follows the same characteristics as an exponential growth because a base of e is greater than 1. Okay, transformations of e to the x are just like the transformations of the other functions that we've worked with throughout the course so far. So example 5, if we were to look at y equals e to the x power, let's say times 3. And then we can even do a plus 1, okay? So this times 3 out front we know is a vertical stretch, times 3, and the plus 1 is a vertical shift, up 1. So if you looked at your table of values, and you can just use the points 0, 1 and 1, e, you're going to change just your outputs. We're going to start by multiplying each of our output by 3. And then what we're going to do is add 1 to it. So this will be 4, and this will be 3e plus 1, which we can actually just write it like that. So when you go to graph this, this plus 1 means that we're going to have a vertical horizontal asymptote at y equals 1, because that's going to shift up as well. And then instead of the point 0, 1, you have that vertical stretch times 3, which would put it at 0, 3, but then shifted up 1 unit. And so that new point becomes 0, 4. And then 1, e, you're going to do 3 times e, which is going to be somewhere between 6 and 9. And then we're going to add 1 to it. So you can plug it into your calculator and actually do 3e. There's an e button on your calculator, plus 1. And it's okay if you write that ordered pair as just 1, 3e plus 1, because that's an exact value. Or what you can do is plug it into your calculator and actually get your decimal value. Okay? And you can see that that continues to be an exponential growth. Okay, and the last one we're going to look at is example 6. It's going to be y equals e to the negative 0.25 x power. Okay, so we can look at our table of values. Here's x, here's e to the x. We have 0, 1, and we have 1, e. Now I want you to think about, in terms of our transformations from the beginning units, what does it mean to have a negative inside the function in front of the x? That means you're going to have a horizontal reflection, meaning that it's going to be reflected over the y-axis. So it's actually, instead of going to be looking like an exponential growth function, it's going to look like an exponential decay and actually end up being an exponential decay function. And then the 0.25 in front, remember what that means. That means technically it's a 1/4 in front. So if we were to undo dividing by 4, we'd actually be multiplying by 4. So we're going to have a horizontal stretch of times 4. So what we're going to do to our x value, since everything is being done horizontally, we are going to multiply by a -1, and then we're going to multiply by 4. Or you can just do it all at once. 0 times -4 is still 0. 1 times -4 is -4. So in this one, you're actually still going to have the point 0, 1. But now we're going to have -1, 2, 3, 4, E. And it's going to look like that. And we're still going to have this horizontal asymptote at y equals 0 because we did not have a vertical shift up or down. So what you can see is that this was stretched horizontally, so it's going to be wider. And you can also see that it's now a decay function because of that negative inside the function e to the x. Because it's decaying. The values are getting smaller as you're going left to right. Okay, so now what you should do, now that you've taken the notes, is go back and just listen to them, and then you can go ahead and get started on homework number 3.